Hello everyone, this is lecture 38 of PEC about the substitution theorem. The concept of the substitution theorem is that for any circuit, including the linear circuit and the nonlinear circuit, if the case branch voltage UK is known, we can use an independent voltage source UK to replace the branch element without changing any other branch variable in the circuit. Of course, if the case branch current IK is known, we can also use an independent current source IK to replace the branch element without changing any other branch variable in the circuit. It's an amazing theorem. Why is it reasonable? We will prove it later. This is the circuit model of the substitution theorem. This is the case branch voltage, and the element is arbitrary. If its voltage UK and current IK are known, it has two forms of the substitutions. In the first form, the element is substituted by a voltage source whose voltage is UK. We are sure that the branch current IK must be unchanged, and any other branch variable in network A must be unchanged. In the second form, the element is substituted by a current source whose value is IK. The branch voltage UK must be unchanged, and any other branch variable in network A must be unchanged. Then we will prove the substitution theorem with the knowledge of the equipotential point. This is a case branch. We and a voltage source in series with the branch and another reverse voltage source in series with the branch. It seems that the branch is unchanged after adding two voltage sources seen from network A. If we define this point as C, we will find that A and C are the equipotential points, because UAC equals positive UK plus negative UK, which is equal to 0. According to the previous lecture, any resistor between the equipotential points has no effect on all branch variables. So we connect A and C with a short circuit line. Now the circuit becomes two sub-circuits. This is the first sub-circuit, which has no effect on another sub-circuit. This is a second sub-circuit, which has no effect on another sub-circuit either. In other words, the two sub-circuits have no effect on each other. Let's focus on the second sub-circuit. It's just the circuit whose case branch is the voltage source UK. We've proved that the branch element is replaced with the voltage source UK without changing any branch variable in the circuit seen from network A. The current is still IK, and all branch variables in network A are unchanged. You may find that the substitution theorem is applicable for both linear and nonlinear circuit. Now we use a linear voltage divider circuit to emphasize the essence of the substitution theorem. In a circuit, the port voltage is defined as U, and the port current is defined as I. So, seeing from the port to the left, the port voltage current relationship is U equals US minus RS times I. Seen from the port to the right, the port voltage current relationship is U equals RL times I. Since the definition of the port voltage and current has no difference in two relationships, they can be both drawn in one figure. The horizontal axis represents I and the vertical axis represents U. In this equation, when I is 0, U is equal to US. when U is 0, I is equal to US over RS. The U voltage current relationship can be represented by a straight line across these 2 points. This voltage current relationship can be represented by a straight line across the origin point. Their intersection is the operating point of the whole circuit. The concept of the operating point, or Q point, will be discussed in next week's lectures. The corresponding current of the operating point is US over RS plus RL, and the corresponding voltage is RL over RL plus RS times US. The essence of the substitution theorem is the intersection of these two lines is still this point if the element is replaced with a voltage source. Similarly, the element can be replaced with a current source whose value is US over RS plus RL without changing this intersection. Furthermore, the element can be replaced with such a nonlinear resistance without changing this intersection. The element can be replaced with such a nonlinear resistance or another Thevenin equivalent circuit as long as the intersection is unchanged. The essence of the substitution is the operating point is unchanged before and after the substitution. At the end of this lecture, we have a note for you. The substitution must ensure the single solution for the circuit. We take two circuits as examples. The first one is simple. We can solve all the branch variables easily. This current is 1 ampere, and this current is 2.5 amperes. According to the KCL, the current is 1.5 ampere. If this branch is replaced with a 5 volts voltage source, what's the problem? Although we know the current is 2.5 amperes in this subcircuit, we cannot solve the value of I1 and I2 based on the KCL and KVL in this condition. In other words, the circuit after the substitution doesn't have the single solution. The second circuit looks strange, but it obeys the KVL and KCL. The voltage drop from A to B is 1 volt. The mesh current in this direction is 1 ampere. Of course, the voltage source can be replaced with a 1 ohm resistor without the change of the operating point of the circuit. But there will be a problem if it is replaced with a current source. Although the mesh current is still 1 ampere, the voltage across it cannot be solved. You should notice that the substitution must ensure the single solution for the circuit. Okay, this is the end of this lecture.